When looking at rates of change, the most typical rate of change we talk about is speed. So when we're looking at speed, we're comparing the distance that a particle has traveled or an object has traveled with respect to a certain amount of time. So when we're working with calculus, we can use this to describe these rates. So what we can do is we can describe the movement of a particle using special words. And when we're looking at speed in this way, we're talking about the displacement, velocity, and acceleration of an object. So in science, you would have looked at values that are vectors and values that are scalars. So vector meaning that the direction and the magnitude of whatever it is important. A scalar value is just about the magnitude. So if I talk about the speed of an object, I'm just saying how fast it's traveling, but not what direction it is. Whereas when I use the word velocity, I'm talking about how fast, but also in which direction we're going. So for the most part, the rate of change and the displacement of an object, we deal predominantly only in one dimension. So one dimension meaning that I'm going to have a line and this particle is just going back and forth along the line. So we're not throwing it outwards. It doesn't have two dimensions on it. So think of it kind of like, if you've got a spring and it's just going back and the ball's going back and forth on that line. So when we're looking at the equation when we're working with displacement, velocity, acceleration, usually for displacement we use the letter x and it's in terms of t. Now this can get a little bit confusing because what we're now doing is when I draw out my axis, time is going to be along the horizontal and x is going to be along the vertical. That's going to be weird for you because we're used to the vertical axis being called the y-axis, okay? And x is usually the horizontal. But in these sorts of questions, our dependent variable is actually the x, and the independent variable is the time. So we specify a time and then we measure the displacement. So that's why we use x on the vertical axis. And you saw that written in the examples that you had to work through last lesson. So let's just go through the terminology first. So when we talk about the displacement, it's the signed position of the particle with respect to a certain reference point. So basically it's saying how far this particle or this object is from a reference point, or we usually call that the origin. So from 0 or O, the origin, how far is it away? And we also give it a sign. So it could be either positive or negative. Or it could be up and down. So usually when we draw these questions, it will be on a horizontal number line, and then we've got O in the middle. So if my particle is over here, then we say that that's positive. If the particle is on the left-hand side, we usually say it's negative. Okay, if we draw it the other way, so if we do it vertically, and we've got the origin in the middle, like with normal convention, if it's above the 0, the origin, then we call that positive, and if it's below the 0, we call that negative. When we go to look at velocity, the velocity is the signed speed of the particle. Okay, so it's sort of like telling us which direction it's going in and how fast. So if my particle is moving this way, then we can say that it's got a positive velocity, okay, because it's moving towards the right. If it's moving towards the left, then we say that the velocity is negative. So we could have the same speed, so I could be going 3 meters per second towards the right, so then the velocity is 3. If I'm going 3 meters per second towards the left, then I would call that negative 3. Likewise for up and down, if I'm moving upwards, then it's positive. If I'm moving downwards, then it's negative. The last one that we look at is acceleration. So the acceleration is the magnitude and the direction of the force that's pushing the object. So think about if I'm pushing, so I'm pushing this way, then this particle can be traveling in that direction. Okay, so if it's already traveling towards the right, if my push is towards the right, then this object is going to get faster and faster. Okay, so think about in a car, if you push the accelerator and you just keep your foot on the accelerator and you just leave it there, you're going to start moving faster and faster because your acceleration is positive. So the force is pushing the car so that it's traveling faster. But what we could also look at is maybe we could be pushing forward, but we might have originally been traveling backwards. So if we were originally traveling backwards, but then there's something behind me pushing me forwards, what's going to happen is I'm going to slow down, okay, because the force is going to force me to slow down until a point where I sort of stop, and then the force is going to keep pushing me forward. Okay, so when we're looking at acceleration and velocity don't have to be the same value at exactly the same time. Okay, acceleration is talking about the force, so is it pushing you forwards or is it pushing you backwards? Velocity is the actual direction that you're actually moving. Okay, now how these all relate to each other, so we know that velocity is a rate of change of the displacement. Okay, so what that means is if I want to find the instantaneous velocity, then what I want to do is differentiate displacement. And we have a way of writing this out. So if we use x in terms of t, so x for displacement, okay, and we're using x, then if I want to find the velocity, that's going to be dx dt. Okay, we're differentiating x with respect to time, and you can see that in that equation there. Another way that we write it is using a dot. Now, if you remember back to that first lesson on calculus, when we first started differentiation in that introduction, I talked about 3 different ways that we write out a derivative. So we've got the dx dt notation, we can use like y dashed, f dashed x. The other one that we haven't really looked at yet is this one here with a dot on the top. So Newton was the one who came up with this because a lot more of the motion-y sort of stuff that we're doing right now, he was the one who did a lot of research on it. So Newton's notation for derivatives is an x with the dot on top, and that's for your first derivative, so dx dt. If I want to find the acceleration, often we will use the letter a for acceleration, or the acceleration is the rate of change of your velocity. Okay, so if I differentiate the velocity, I'll get the acceleration. But because the velocity was the first derivative of the displacement, I could also call the acceleration the second derivative. So if I take displacement and differentiate it 2 times, then I'll end up with the acceleration. Now, using Newton's notation, that's going to be x with 2 dots above it. Okay, so double dot meaning there's 2 derivatives with respect to time. So the only times we use these dot notations is if we're differentiating with time. Okay, so we don't just use them wherever we want. For most of your typical differentiation questions, you will be writing them as like dy dx or y dash f dash x. Okay, it's only when we're talking about motion that we do use these dots. Okay, so let's have a look at an example. So the displacement x centimeters of a particle over time is given by this formula here. So x equals to 4t minus t squared. First question, find the position and the velocity of the particle after 1 second. So what we want to do first is, because we are asked to find the velocity, first thing we'll always do is differentiate. We're going to find everything that we need first. So we're starting with x equals 4t minus t squared. So the velocity is going to be that differentiated. So if I differentiate 4t, that's going to be 4 minus the derivative of t squared is 2t. So those are the functions, so that's the equation to work out the position and the velocity of the particle. So when t equals to 1, we're going to work out what x and v are. So x, your displacement, is 4 times 1 minus 1 squared, which is 3. So this particle is going to be 3 units to the right of the origin. The velocity is 4 minus 2 times 1, well that's 2. So the velocity is 2, and we need to work out the units. So displacement, so x was given in centimeters and time was given in seconds. So when I worked out the displacement here, that's going to be in centimeters, and the velocity is going to be centimeters per second. Okay, it's important that you know what units you're working in, so centimeters per second. Now, those of you who do physics, you might have seen that also written as cm minus 1. Oh, sorry, cms minus 1. Okay, the minus 1 just means that this is like a fraction. Okay, so think of that like if we look at it like an index, then that's like saying cm over s, so it's centimeters per second. Okay, so that's just different ways that we can write it. Oh, and also anyone who does physics, displacement in physics is usually written using the notation s. Okay, s for displacement. I don't know why s, but they just chose to use s. So sometimes you might see x, sometimes you might see s. For most of mathematics, we do tend to use x a lot more. I think it's just our usual go-to pronumeral. That's why. Okay, so just know that both of those will usually mean displacement. We do use v and a for velocity and acceleration a fair bit. Okay, part B, find when the particle is stationary. So if the particle is stationary, that means there's not going to be any speed. So we want to solve v equals to 0. So when the velocity is 0, the particle's not moving. There's no speed, there's no velocity. So if we substitute that into that equation there, then 4 minus 2t equals 0. Negative 2t is negative 4. Divide both sides by negative 2. T is equal to 2. So after 2 seconds, this particle is going to stop moving. Okay, and then it's going to do something afterwards. Okay, next part, find the distance traveled by the particle in the first 3 seconds. Now note, I've used the word distance here. Distance is a scalar value. Okay, so scalar value meaning I'm just finding how much altogether. I'm not looking for displacement. So displacement is how far from a reference point. Distance travel is just the whole thing. So say, for example, if you're talking about going to school from home and then going home again, if you want to talk about your displacement when you reach home, your displacement is actually 0 because you're back at your starting point. But if I talk about the distance traveled, you went to school and you came back, you're going to be looking at the distance to school doubled. Okay, so that's how displacement and distance are different to each other. Now this is really important because if we're looking at the first 3 seconds, over here, remember we know this particle or this object stopped after 2 seconds and then it did something afterwards. So what we need to do here, sometimes this actually helps with, if we did part D first actually, if we drew the graph, that actually can help us when working out this distance traveled. So I'm actually going to start with part D first. So part D equation was x equals 4t minus t squared, and basically we're sketching this. So think of that, it's kind of like having y equals to 4x minus x squared, and we're graphing that on a number plane. Now when we go to graph it, we always take t to be a positive value. Okay, so we don't usually do anything with this negative bit. Okay, so only t for positive, and x is going to be on your vertical axis. If you look at this equation, that's actually a parabola. So if I take t out as a common factor, 4 minus t, okay, so from there we can see that x equals 0 is going to, so t equals 0 is going to be an intercept, and if 4 minus t is 0, then t equals to 4 is also going to be an x-intercept. So what this graph is going to be, it's going to be an upside down parabola. It's going to go up and then back down. Now we can talk about negative displacement, so that's perfectly fine. So we'll just leave our graph like that. We know from part B that the graph is stationary. That point there is at 2. So effectively what this is showing is when we put the time axis here, remember what we were talking about before, this particle is moving along just a vertical line. It's only a one-dimensional line, okay? So when I look at what's happening here, it's going up and back down like this. It's not actually moving outwards, it's actually going up and then back down, okay, on the exact same line. So that's actually what's happening to this particular particle. But what we're doing is we're stretching this out on a time axis. So think of it as I'm taking like bursts of the particle as it's moving, and then I'm putting all those burst pictures next to each other. And that's how you're going to get this sort of graph come out. Okay, so it's sort of like if I stretch it out, then that's how I end up with this graph here. So that's your graph of the displacement versus time. Now, if we go back to part C, we were looking at the value 3, I want to work out the total distance traveled. Now, what's happened to this particle is it's gone up to 2, and then it's traveled back down to 3. So what we need to do to work out the total distance traveled is, because we know that the particle stopped here, we need to work out how far it's traveled here. So how much is traveled to get up to the highest point, and then we need to work out how much it took to get back down to where it's equal to 3. So what we're going to do here is we're going to work out, so when t equals to 2, we're going to work out the x value, because that will tell us this vertical height. And then what we'll do is we'll work out what the distance is when t is 3, and then we can work out that difference. So when t is equal to 2, then x is 4 times 2 minus 2 squared, which is 4 units. So what's happened is, in the first 2 seconds, in this bit here, the particle's travelled 4 units up, and then it's going to travel back down. So we need to work out how much it's travelled down by. So when t equals to 3, we're going to calculate x. So it's 4 times 3 minus 3 squared. That's 12 minus 9, which is 3. So if I draw it on here, I'll just rub out all my highlights. So what we're looking at here is this particle, the highest point there is 4, and then it drops to 3. So this particle has gone up to 4 and then back down to 3. So then the total distance travelled is going to be 4 plus 1. Okay, so 4 units to get to the top, and then 1 unit to get down to that point. So the total distance travelled is 5 centimeters. So when we're looking for the distance, it's really important that we find where this stationary point is. For most of the questions that we'll be working with for the time being, they will scaffold it. So they'll give you the steps to work through it. Often a diagram is actually quite useful, and that's why all the curve sketching we did earlier in the year is very, very important. You need to be able to identify equations and to be able to sketch them on a number plane as well. So the questions that I want you to do are just down here. I've put the answers over here. Hopefully, it's not going to be too distracting. So if you could work through those questions. For the sketching questions, I haven't provided you with the answer, but what you can do is you can put those equations into graphing software. When you put it into graphing software, you'll change the S into a Y, and then your T values will turn into X's. So you still write out an Y equals X sort of equation, okay? And remember, we're always taking T to be positive. So we're only looking at the right-hand side of the axis. So if you could give those questions a go, if you need any help, make sure you ask.